Kia ora, Year 12. This is the last part of the long question on vectors from the 2017 May paper. So we've already done in parts 1 and 2, these first two parts here. We had to find the position vector of the foot of the perpendicular, and then we had to reflect that. And we had to find the equation of the plane through the origin containing a line. So in the last part, we're asked to find the exact value of the perpendicular distance of A from this plane. So just a really quick recap. We had point A, which was here, and then we've got the origin. We've got a line off here, and we drew a plane that was going through the origin and including that line. And we found in part 2 that the equation for this one was, depending on how you wrote it, we ended up with x plus y minus z equals 0. Okay, so that was in here, and we know that point A has got coordinates 1, 2, and 4. So part 3 has two ways of doing it. One of them is really, really easy. If you remember how to use a formula for the distance from a point to the plane, this is a very, very fast question. But I'm going to do it two different ways in case you forget that in the exam. And I think it's a nice example of how we can use what we've learned so far. So the formula for the distance from a point to the plane looks like this. If my point is alpha, beta, gamma, and my plane is N1, then the distance is equal to this. So it's the absolute value of alpha N1 plus beta N2 plus gamma N3. I don't know why I wrote them that way around. That was a little bit counterintuitive, but there you go. In other words, what I'm doing is I'm taking the values of my point and I'm just substituting them into my plane equation and subtracting off my constant, okay, and taking the absolute value. And then I'm scaling that by the magnitude of the normal vector. So that's the perpendicular distance from a point to the plane. So we can do that straight away on this and get our answer. So my point here is 1, 2, 4, and my plane is this. So the distance is equal to 1 plus 2 minus 4 minus 0 divided through by 1 squared plus 1 squared plus negative 1 squared. So what does that give me? Well, the numerator works out to be 1 over the square root of 3. So we're done, right? So very, very easy. But I'd like to go back to sort of first principles and look at how we could do it if we forgot that. Right, so we've got a point A, and it's got a position vector of 1, 2, and 4. And we've got our plane of x plus y minus z is equal to 0. So we know that the direction vector perpendicular to that plane is 1, 1, and negative 1. So if we want to do the line that's perpendicular to the plane through A, we can easily write its vector equation, and that's r equals 1, 2, 4 plus lambda with the normal direction vector. So to figure out the value of lambda where the line is going to meet the plane, so there's point A, and here's my plane. Right, so I'm trying to figure out where will this point hit the plane. We're going to solve for lambda by substituting back in here. So this is 1 plus lambda, 2 plus lambda, 4 take away lambda. So that's my x, y, and z. So we substitute back in now, and we get x plus y take away z equals 0, 1 plus lambda solving that gives me 3 lambda equals 1. Lambda is 1/3. So that tells me this point of intersection of the line and the plane, we'll call that C, has got the following position vector. 4/3. Right, so I'm taking this now and substituting in there. 4/3, 7/3, and 11/3. All we have to do is to find the distance between A and C. So from A to C, breaking my rule of never doing a diagonal line for my fractions. So A was 1, 2, and 4. So that's 1/3, 1/3, 1/3, and -1/3. And you can see even from looking that we're going to end up with, thankfully, the same answer. So the length of that line is equal to this. Which is the square root of 3/9, which equals 1/√3, which is what we got before. All right, thanks for watching. I'll do some more vector videos, but probably not for about another 4 or 5 days. So if there's anything special that you want done, just send me an email and let me know.